It's my distinct pleasure and honor to introduce Dr. Chris Jones, who comes to us via Imperial College, where he did his bachelor's and PhD in chemistry. Recently, though, he comes to us from Edwards, where he's been working closely with MIT.nano. Almost all of our abatement systems are from Edwards. Chris and I were just talking a few minutes ago. He is very big in the semiconductor industry consortium's PFAS area. So what we'd like to do is share with you Chris Jones and his expertise in the semiconductor manufacturing area. And I was asked to introduce him, not just because I work in MIT, but also because we have been working closely with Chris in our FUTUR-IC program, which is an NSF-funded program for bringing resource efficiency to semiconductor manufacturing and operation. So it's very important for us to look at all angles of how to minimize PFAS, whether it's through etch processes or whether it's through wastewater, however it is. PFAS is not good for the environment, it's not good for us, it's in all of us, and we need to find ways to minimize the negative impacts of PFAS. He's worked very closely with our team to do handprint initiative, which is different than footprint. I don't know if he's going to say anything about that, but basically, But you know, the good news is that PFAS is now being talked about. And once you find a problem and you define that it's an important thing to get rid of, hopefully it'll be a global effort to make this a clean planet. Thank you. Welcome.
Thank you very much. I'll dwell on the front slide for a little while because you'll see quite a few names there. Most of the work in this presentation has been done by my colleagues. My role is largely around awareness. I'm at an age now where I sit behind a computer creating documents a lot, but they're quite interesting normally. So the work has been done in our lab just south of Bristol in the UK and at one of our facilities in Korea. That will probably become a little bit more clearer later on. The Edwards, as you've just described very well, we sit in the fab in various places, from the clean room with our turbomolecular pumps and chillers, to down in the sub-fab to our pumps and our abatement, but enough of the sales pitch. So what are we going to do today? I'll spend a bit of time on awareness. That's my role in life. What are PFAS? This is very much aimed at a general audience. So none of what's going to be discussed here is technically challenging and won't go into substantial depth, but it is relatively broad ranging. So what are PFAS? Key environmental parameters and health impacts. Some of the regulatory frameworks. I was just being asked what's going to be the driver. Is it going to be public outcry or regulator? And the answer to that one, well, depends where you are. The industry response. The industry often tries to get ahead of things by doing things voluntarily before activities are imposed on it. And how that industry response has actually been manifested in some health data, actually. Then analysis. I'll briefly touch on analysis. The conclusion to the analytical section is basically you can't do all the PFAS with any one technique. You're going to have to, there's a lot of work to be done on analysis and waste treatment. The two are intimately tied because if you don't know if you can't measure something, you can't work out whether you're actually successfully treating it. Then the studies on our own sites, water and wastewater. Some abatement characteristics. We've been looking at passing PFCs through our abatement. We've been looking to try to mimic chambers and passing byproducts from sort of chambers into our abatement. And then some deposits that we found on pumps that have been returned to us from fabs themselves. So these are deposits from essentially real high volume manufacturing situations. And then something on operational controls. It's something we've all got to do. There are laws by which we have to report PFAS being moved around the world, especially into the US at the moment. So I'll describe some of the activities that we're involved in there. So it is broad-ranging, deliberately broad-ranging, with the goal of trying to open everyone's eyes here to that there are many people involved, many functions involved in ensuring that we manage this particular challenge. PFAS, what are PFAS? Polyfluoroalkyl substances. The US EPA has a definition largely around whether there's presence of C₃F₂ or C₃F₈ groups. The OECD definition, which up until 2021 was used by the EU, a similar definition but without any heteroatoms in it. The OECD are probably going to change their definition sometime soon that may expand the 4,000, 5,000 compounds that they're looking at. I'll come on to some of the numbers a bit later on. Why are they used? Well, they're thermally and chemically stable. So if you're in a highly challenged environment, that's quite a good thing. They're often quite slippery, and that's a property that is often desired in process use, and they don't tend to leach. So if I've got PTFE pipe, PVDF pipe, then you don't find very much leaching into the pipework. So for ultra pure water situations, those sorts of materials are commonly used. As far as the fab is concerned, these are used in photolithography and photoresists, in etch and deposition processes. It depends how broad you want to go on what's a PFAS, what isn't a PFAS, but in etch and deposition processes, some of the gases used may not be classified as PFAS. In equipment components, I've just already mentioned PTFE, PVDF, PFA, Viton, Calres, materials like that. Heat transfer fluids. Many of the heat transfer fluids are PFAS and need to be PFAS in order to keep the chillers the size that they are. We're moving over, because of various regulations, to different materials, different gases, but they can often represent different challenges. And then lubricants and sealants. Our own pumps contain a perfluoroether, and certainly we use sealants that are PFAS at the moment, but we use them primarily because of the aggressive environment in which we're operating. Various parameters that are used to study the impact in the environment will include things like persistence in water, persistence in the body, whether it's mobile, whether it is toxic, whether it's bioaccumulative. I've deliberately picked out 6 PFAS here. These were the original PFAS listed by the US EPA under the drinking water standards. I think that it's probably going to change fairly soon, but these were the ones listed. And I've basically plotted their parameters on a radar plot with regards to those various characteristics. And what you can see, the red shape is essentially where things sit on average. The grey shape is the error bars around those particular properties. The Gen X and the PFBS were proposed as alternatives, but even they have their problems. And PFOS and PFOA come under Stockholm Convention. I think it's about 40 odd countries have signed the Stockholm Convention, so those are highly regulated already. Why is this important? Well, if these chemicals can move, if they can bioaccumulate, then they can get into us. This is one study which looked at PFAS through the food chain. It starts with some vegetables, so soy, corn, wheat, leafy veg, and then animal products, milk, cheese, chicken, pork, beef, and eggs. This, I need to stress, is from an area where there was PFAS contamination in the soil. So this is a PFAS contaminated region, but what you will see is that if you have chickens that are eating leafy veg that you grow in your garden in a PFAS contaminated area, then chances are the eggs are going to be rather contaminated. I presented this slide, possibly ill-advisedly, just before lunch at a conference earlier in the year, and nobody seemed to be touching the eggs. So one example of bioaccumulation. If a material ends up in a plant and then moves into an animal, and that animal is eaten by another animal, and as the PFAS is accumulated through that chain, that's called biomagnification. But this is just another study, and from worms to mussels, various wildlife, different organs, protein-rich organs, so the brain, the liver, etc., tend to be areas where some PFAS will tend to concentrate. I'm going to come back to the human serum comment in a little while. It's a good measure. There's been lots of studies with regards to how that has changed over the years. The importance here is essentially if we have species that are predators, then generally speaking, the predators will be eating species that are themselves contaminated, and it's a different route to mobility. The effects, what I would stress here is, although this is a relatively large set of studies, or actually the greater list of references is rather more extensive, this is still a relatively small number. This work is ongoing, it's very early, and the analytical challenges that I'll probably come on to occur throughout all of these types of studies. So if there's immune suppression, endocrine problems, liver challenges, thyroid and reproductive issues, these have been studied. They are of statistical significance within the study, but how do you then try to correlate with the presence of PFAS if the analysis of PFAS is still at a relatively early stage? From a regulatory viewpoint, I'll work my way up from US EPA COMTOX database, which I think is currently standing at nearly 14,000 chemicals. The OECD, it's what the Europeans currently use, has about 5,000. If I go to the toxic release inventory regulations here in the US, it's 200 PFAS. If I move to the REACH regulations in Europe, 75, and then the Resource Conservation Recovery Act, RCRA, has 9 listed. And when I did the slide, drinking water had 6. We're gradually moving closer and closer to us. So we all drink drinking water. So as this narrows, so we're beginning to focus now on high-risk PFAS. And certainly the risk assessments, the methodologies used are going to become increasingly important as we move forward. It's all about really what matters, but I'm not entirely sure that we're well versed in what matters yet. Key considerations for the policymakers. I've mentioned persistence, bioaccumulation, toxicity, and mobility, etc. What scope are we going to use? Europe's got its 5,000. If they change to the revised OECD limit, then that will go up several orders of magnitude. US EPA currently 15,000, 20,000. The regulatory frameworks really do vary around the world, and that's a bit of a problem. There needs to be a significant degree of harmonisation. Stockholm Convention helps, but the Stockholm Convention is usually where things end up relatively gradually rather than broader policy. Industrial use and essentiality. Is it really essential to use? I'll put my hand up and say we've used PFAS in some of our products because it means we don't have to redesign the product in order to accommodate a different material. Now, of course, we're looking to change that particular policy. I'll come on to that in a little while. Testing and monitoring. There are methods. US EPA has issued a method, 1633. Some would say it's probably in a bit of a rush, but there are methods around. But those need to be improved. And certainly the availability of the various techniques that I'll come on to in a little while in a very outlined way is not universal. We, for one, can't get most of the techniques readily available in commercial labs in the UK. We have to hunt a little further afield. Economic and technological challenges. If I have to incinerate at 1100 degrees C, that's great for hazardous incineration, but what's the capacity of hazardous incinerators, and are there enough? The simple answer to that one is probably not. Alternatives and innovation. There's certainly a lot of money in the well-developed countries for alternatives, innovation and research, less so in the less well-developed countries. And most of the papers that are produced here, being mentioned here, are papers that are citing studies that aren't done in Africa, that aren't done in South America. So there's definitely an economic mismatch globally. And then final, global coordination. The Stockholm Convention offers a degree of coordination with regards to persistent organic pollutants. Not all countries are signatories. Most countries sort of follow the general trend. But with regards to the management of PFAS, especially if there's 5,000, 10,000, 15,000 different PFAS, the management of PFAS needs greater global coordination. So what's the response of some industries been? Back in 2003, M voluntarily looked to phase out PFAS. And then in 2006, the EPA introduced a PFOA stewardship activity, and the EU started banning PFAS in finished products. 2013, DuPont took their lead and ceased PFOA production. And 2017, PFOA then was cited under REACH European regulation. 2020, further activities under Stockholm. 2023, the EU banned PFHXA. The HX stands for 6 carbon atoms per fluoro. The acid on the end, carboxylic acid, was banned in 2023. And then the drinking water specifications that I mentioned earlier on were finalized, I think, in March 2024. There has been an impact. The regularly blood serum is monitored during operations for PFAS, and what you can see is PFOS was the major PFAS present in blood serum back in 2000, and that's been gradually dropping as we move to 2016. I've tried to find a more up-to-date version of this, and I haven't been able to. The other PFOA, PFHXA, PFNA, those have started from lower points, but are sort of dropping far less quickly. And there's certainly a recommendation from the various medical institutions with regards to what you do and what levels, what are the action points. And at less than 2 nanograms per mil, now you'll notice I've suddenly jumped to nanograms per mil. I'm going to be talking about nanograms per litre in a while. No action is needed. Follow standard healthcare rules. 2 to 20. We ought to be looking where they're getting exposed, and that's especially true if we're talking about pregnant ladies. And at greater than 20 nanograms per litre, there's really urgent action needs to be done. We should be looking for signs and symptoms of problems in the thyroid, in the kidneys, testicular cancer, colitis, etc. Should I be concerned? I've certainly attended quite a few conferences recently where it seems to be very in vogue to send your blood off for PFAS analysis, and folks will present it. Is it a good thing? I think awareness is a good thing. If it's just fashion, I suspect that's not the case. On the analysis side, I mentioned US EPA method 1633. LC tandem mass spec. It's certainly the method we've been using, not 1633. We've been essentially looking at a derived version of the older 537 with a rather broader range of standards, but nonetheless, that's certainly the method we've been using for our wastewater. Air and volatiles, OTM 45 and 50, derived from essentially from semi-volatile methods. Blindingly expensive to get done. Would love to get it done within the projects that I tend to be active, rather more difficult to justify. Total oxidizable precursors, and then the various other methods mentioned here. A good a good reference for review. I've listed most of the references, and the slide deck will be available afterwards for folks. So a nice review. It also then follows through to various other reviews. But the bottom line is 40, 50, 60 standards are on 1633, 5,000, 10,000 different species, 200 within TRI. There are some big gaps. OTM 45 and 50 in air, rather expensive. I certainly couldn't justify it for our work, although we are looking to use time of flight mass spec probably early next year to do gas phase measurements. Lots of work to do. There's some major differences depending on how you do the analysis. There are probably differences based on actually sample quality, whether you're getting micelle formation that then makes the technique blind to your method may be a problem. It's not my area of expertise, but there are certainly challenges moving forward with analysis, not just the gaps, but also the consistency. In waste treatment, generally speaking, the gold standard seems to be treated as hazardous waste. So high temperature incineration, whether it's 1100, 1200 or longer term train type methodologies, you gradually increase the temperature of the material. At the moment, high temperature incineration seems to be the way, seems to be the accepted method relatively globally. In wastewater, granular activated carbon, ion exchange, reverse osmosis, all methods that are used, but as soon as you start getting very large volumes, you're going to start accruing substantial costs. A way of treating supercritical water oxidation, familiarity with this from 25 years ago when it was proposed and used for chemical weapons treatment. They had challenges with regards to corrosion of their vessels. They also had scaling challenges. SCWO was, neutralization in SCWO was highly effective, but it certainly had its barriers before it became implemented. Electrochemical oxidation, as an electrochemist, I worry about this because it's surface area driven, it's diffusion driven. Can you get down to very low levels? That worries me. I've studied electro-oxidation for various contaminants quite a few years ago, and it can be effective, but can you get down to a nanogram per litre? Probably not without adsorption concentration technologies. Liquid chemical concentrates, basically off-site hazardous combustion. We're back to combustion. Can you absorb and combust? On the gas side of things, thermal oxidizers at the right temperature. Well, I'm hoping I'm going to demonstrate that's probably the case today. The challenges are verifying the DRE, and certainly the data I'm going to show you today will demonstrate that we've certainly had difficulties maintaining any sort of carbon-fluorine mass balance. So moving forward, the capture technology then needs to treat, you're always going to get secondary wastes. How do you treat your secondary wastes? So if residuals are there, do they get destroyed there? Do they get managed somewhere else? Combustion, okay. Landfill is accepted, but there are lots and lots of caveats with regards to landfill. How do you ensure there aren't any leachates? If there are leachates, how do you manage them? If there's off-gases, how do you manage them? We're back to the secondary waste challenge. As I said, promising is QO for biosolids, SCWO for biosolids, RO for brines. Ultimately, you still end up with secondary wastes. You're probably invariably heading towards incineration as a primary method of treatment. So, what are the worries? The worries are, and certainly there have been reports in the media, incomplete destruction, or does incineration offer a complete destruction? Extensive studies going on in a relatively limited number of sites, that will have to continue. And then capture-only methods, what are you going to do with the waste? We're sort of heading towards the secondary challenges that we also have, say, in the nuclear industry. What do you do with a PFAS-laden waste? Probably incinerated at the moment. So that's the awareness side. If I move on to our own testing, these are the compounds that we've been analysing for in water. I need to stress all of our work to date has been done in water. Not all of these analytes have been targeted in every single sample. We have 2 labs we use for 3 different types of analysis. What we refer to as a high limited detection at about 100 nanograms per litre, medium limited detection at about 20, and low limited detection down at about 1. I've plotted for the various species the limits of detection, and there is some variation there, but essentially this is what we will refer to as high, medium, and low limited detection analysis. And some of the samples I'll be showing you are definitely in the low, and some of the samples I'll be showing you needed dilution to fit in the high. A bit of a recap. Back 2 years ago, almost 2 years ago, I presented at C₃ Why do we use PFAS? The bottom O-ring that had disappeared was nitrile in 20% fluorine for not very long. The Calres FFKM O-ring survived. Where are PFAS used? In all sorts of places, from pipes and tubing to tape to insulators to liners and diaphragms. Within our own service technology centres, how do we manage PFAS? Well, O-rings are sent to hazardous waste incineration. The oil is incinerated or recycled, and about 69% of our PFAS waste in total was from oil, with 70% of it off to hazardous waste incineration. We did some testing at a fab in Europe where we were experiencing a liquid in the pump exhaust. It was causing problems with the service interval, and we were brought in to look at essentially what's the problem. After a lot of toing and froing, we identified it was a perfluoroether, and our first port of call was it must be the oil out the pump. But the oil level in the pump wasn't changing. So this was on a Bosch process, and actually it was coming from the process. A significant quantity of liquid was coming from the process. But back in 2017, when we were looking at this particular example, this was an MTBS problem. This wasn't a PFAS problem. It wasn't even a greenhouse gas problem. So we urged the operator to put heat trace on their pipes. The material disappeared into the abatement and essentially disappeared. We also, a couple of years ago, did some testing whilst we were looking for the limits of HF. HF removal from waste gases in our abatement systems. We heavily overloaded one of the abatement systems with C₃F₈ in order to push the HF concentration up in order to try to work out what the limiting performance was for HF, and we took the opportunity to look for PFAS. We thought, well, if we're going to see it anywhere, we'll see it when we're maloperating. At the 100 nanogram per litre limit that was imposed on us at that stage, we didn't see anything, everything below limited detection. So that was the work leading up to C₃ in 2023. On our UK site, this is a little bit simplistic. We have water, city water coming into a softening plant, chemicals coming into the softening plant, that feeds our labs. We have city water coming into a small recirculation loop, which is essentially our final test area. That test area involves heating certain PTFE components to quite high temperatures, so we were expecting some challenges here. We have a much smaller test area here, and then we've got a chilled water supply. Everything is neutralized before sent to outfall. If I look at the levels of PFAS in our lab water, this is soft water results. So the red line is essentially the average of quite a few now soft water samples, so that you can see in the nanogram per litre level, we're getting the butyric, we're getting the pentyl up to about 12 nanograms per litre, and then gradually dropping down to, thankfully, very low levels, limited detection for the longer chain, including the regulated PFOS and PFOA. The grey represents variability, 95% confidence limit. The yellow represents our tap water, so the softening system's removing some PFAS to an extent. Might expect that. Ion exchange is used for removal of PFAS, and the green line's essentially the limited detection of the species. All the others were below LOD. But what are we essentially saying? Our water's got PFAS in. If the results are in the grey zone, we can't tell the difference between our water and the results that we're getting. Taking all that on board and redrawing that map, essentially we've got contaminated water moving throughout our system. But as we did suspect, there is PFAS at a higher level here, in the 20 to 70 nanogram sort of range. Noting that UK drinking water specs at the moment is 100 nanograms per litre. There's very few wastewater specs globally. But so we're within drinking water specs, but that's sort of essentially what we were expecting to see. And then to neutralisation and outfall, as I said, it's a small volume discharge before neutralisation. The major water through route is essentially through our lab. This is quite a busy slide. It does two things. One, we're testing C₃F₈, we're testing C₄F₈, and we're testing materials. So do we see anything significant when we're just treating C₃F₈, when we're just treating C₃F₈, or when we're just running blanks? The DRE numbers that are on the picture refer to the conditions required for a C₃F₈ DRE of that number. So if I take the soft water, add up all the non-limited detects, I'm going to end up at about 50 nanograms per litre. Sorry, that's soft water, yeah. If I take the lab blanks, in other words, what's going on in the lab, I don't see anything that's any different. DI water, actually everything was below LOD. Really, I should put, if I follow the rule that I've got in the slide, which is only adding up materials greater than LOD, that really should be 0. But nonetheless, I've put it in there just for reference. But as I go through the various tests, whether it's C₃F₈, C₃F₈, whether I'm using materials PTFE, PFA, or stainless steel or aluminium, might be a little bit of a drop here. But to be brutally honest, at least with regards to the treatment of these particular gases in our abatement systems with the materials that we use, we just can't tell the difference between ourselves and the soft water supply. So, that isn't what happens in a fab. Fabs will tend to be probably generating longer chain species. So our next port of call was perfluorooctane. What happens when we treat a longer chain PFC, PFAS? High fire is 95% DRE. We just don't see anything in the water. These are water results. We just don't see anything in the water. If we take the trouble to bubble PFO through an impinger, we see PFAS in the impinger water. Impingers usually run with DI water, so the PFO is contaminated. I don't think PFO plus water is going to give you hydrolysis. So the PFO actually contains a small amount of PFAS. If I deliberately run in a low energy mode on our abatement and try to treat PFO, I see some PFAS. Not very much, but I see some PFAS. But that's not where I would recommend anyway. If I co-flow PFO and C₃F₈, I do see something. They're quite low levels. It's a log plot. These are quite low levels, but we're reinvestigating this. It took us a bit by surprise. Bearing in mind C₃F₈ on its own, nothing. PFO on its own, nothing. So this one's being reinvestigated. Okay, that's great, but what about getting closer to a chamber? We don't have a chamber. So what we used was an MKS Astron ICP to generate byproducts from C₄F₈. The byproducts themselves were then pumped into an abatement system and water samples were taken. I'm going to show a few diagrams now, essentially the methods. So the Astron to a pump to an abatement, C₄F₈ and argon. C₄F₈ into the pump, C₄F₈ into the pump, C₄F₈ after the pump. Now, we wanted to try to distinguish between C₄F₈ that had been through an Astron or been through a pump to make sure that whether the C₄F₈ itself was contaminated. We have an impinger here. We have the abatement here. Most of the gas goes through the abatement, but some of the gas goes through the impinger, and DI water samples are collected. And then to somewhat replicate OTM45 type methodology, although I will concede you don't usually have your 4 impingers on that. We had DI water, and made a decision to stick caustic in at the end, which was probably a good idea, to do another test. In an ideal world, most of the material would end up in impinger 1, little in impinger 2, very little in impinger 3, more than 10% in the wrong place is essentially a fail. We put the 1 molar in there anyway in case we just saw something, and we did. So now, need to take this graph rather carefully. We had been talking about 10 nanograms per litre. If I now essentially take an Astron C₄F₈, pass the gas through an abatement in low fire, then I end up with 100,000 nanograms per litre in the abatement. So the Astron's producing a substantial amount of PFAS material, and we list the distribution here. Unfortunately, we'd contaminated our equipment. So when we switched to high fire mode and took a blank, essentially the blank and the high fire mode are pretty much the same. The snag we've got is we've ended up contaminating the kit. So experimental order, experimental method is really rather critical. And there's going to be a pointer here to potential how we might want to consider running equipment in future, or at least the question should get asked. So from point of view of contamination, if I was just relying on the drain system to remove ionic contamination, then this is the rate at which I'd expect to see HF decline. Or more accurately, this is the rate at which HF would decline. This was a real test. And then as we sort of move through with time, these are the concentrations of the various PFAS with time, and you can see there's a definite discrepancy. The PFAS are differentially, I'll use the phrase sticky, but still residual within the system. Now the snag we've got is residual where is rather an appropriate question, but ultimately they're residual within the system, and it does take time for them to be released from the abatement. So just a quick rinse isn't good enough to decontaminate. If I look at, I mentioned that we were looking at the C₄F₈ cylinder impurities, and that's exactly what we found. So C₄F₈ is contaminated with PFAS. If we introduce it pre-pump to alter the distribution, we alter the distribution with a greater concentration of the low carbon PFAS. So whether it's before or after rather depends on exactly what we're up to, but that could be a contaminated pump. So again, we have contamination challenges. Moving on to the pump, we ran an Astron plasma for about 30 minutes, turned it off, and 2-minute impinger samples were taken rather regularly over 5 hours, and it took rather a long time for the PFAS to drop back. If we were targeting 10 nanograms per litre blank, it took rather a long time to get back to blank, which we would normally say, if we were abating C₄F₄, that we would have a PFC signal, that if you're flowing C₄F₄, turn the PFC signal on, activate high energy mode. When the PFC is no longer flowing, wait a little while, then turn it off. Might need to at least ask the question, is that appropriate? The answer may be yes, the answer may be no, but the question needs to be posed. It does mean we can see very clearly here how difficult it is to essentially maintain clean systems in order to do low limiter detection analysis. If we clean the astron using an argon oxygen clean, then we get exceptionally high levels of PFAS coming out. Introduction of ozone in the plasma reported very high concentrations, likely formed from the reaction of the plasma with CF polymers in the pump. I'm going to come on to that. That's my last topic, is CF polymers in the pump. And then, earlier on we'd mentioned that we'd set up the system, the abatement system, such that we weren't really getting back down to low levels of detection to determine whether we were getting good abatement. And if we were careful, then what we end up with is this situation. So we're almost back to 10 nanograms per litre. So what we can say here, at least within the limit of the analysis, we're doing a good job in destroying the PFAS that's coming out of that astron. Impinger tests. I mentioned we had an impinger in here. We've got a lot more data than this, but we don't have a lot more time. So I'll concentrate on that multiple impinger test. And what we saw was this. So impinger 1, impinger 2, impinger 3, caustic impinger. And what you can see is a gradual decrease generally in impinger 1, 2, and 3 for the shorter chain. But as you move to some of the longer chain, perhaps that's not applying. Now we don't know exactly how much is being produced, so that's a bit difficult to tell. But in the caustic route, the shorter chain seems to be taken out rather well by the caustic. The longer chain, less so, probably expected from the chemistry. If I look at total mass conversion, and we basically try to run the maths, making an assumption that everything's captured, which undoubtedly it isn't, but let's start with the assumption, then what we've essentially been able to identify is we've got roughly 2.7 MIGs in 15 minutes from the impingers, but from CF4 that would have been 13.4. Most of it, however, is converted to the PFCs, but not all of it. We're about 28% missing. So somewhere in our analysis, there's some CF floating around, probably heading into our pumps, but not being identified by the analytical techniques that we have open to us at the moment. So as of today, as of a couple of days ago, we can set up in such a way that we can, at least within our analytical limits, demonstrate from the astron results that plasma byproduct PFAS is destroyed by the abatement if operated properly. We've also demonstrated a significant degree of contamination problems, as well as there's a CF balance problem. The oxygen plasma was able to remove substantial amount of carbon fluorine deposits from various places, including the pump. But we have yet to determine the effectiveness of that cleaning method. So we'll drive on, and sometime in the next 6 months, there'll be more to report on these particular topics. I said I'd talk about pumps. We often get powdery deposits in our pumps. The photographs here, the photographs here. That's a subatmospheric CVD high aspect ratio gap fill process. It's this one. And this one's a high aspect ratio via etch process is this one. What we saw from EDX was essentially pretty well 100% carbon fluorine deposit. In other words, the white deposit we have here is almost exclusively carbon fluorine. Slightly interesting, if we put it through a TGA, it largely all goes by about 240C, so it's obviously not Teflon, but an interesting point. More recently, we've been using XPS to try to determine some of the species, and some of the species have essentially been identified here. So we are getting CF2 polymers in these materials. But what we did was we then took some of the samples and sent them off for conventional solid PFAS analysis. This is the blank. It's the best we could find with as little carbon and fluorine in it. Then the 100% one that I mentioned previously, then one at about 90%, and then one at about 60%. That was a liquid, so it was gathered on wipes and sent off for analysis. And this is what we see. So in that one that was essentially 100%, we're seeing levels of 10,000, 100,000 nanograms per kilo, gradually increasing as we move up in molecular weight, and then again as we move up in molecular weight. Similar sort of behaviour for the other etch, to an extent a little bit similar for the liquid sample. The low sample had very low. The low sample had very little PFAS in. The challenge we've got here, though, is although we've said 100% of that white sample was carbon fluorine, we've been able to identify less than 0.1% within standard solid PFAS analysis. Granted, there are other techniques, but this was the one that was open to us. So there's a lot of work to be done there. Going on to operational controls. Got lots of sites. Some of them are service technology centers, some of them are product companies. The pumps, obviously the pumps that we've just been talking about have been sent to a service technology center. The service technology center are essentially designed to handle hazardous materials coming to them. So it's no great surprise that they have the techniques in place in order to manage hazardous deposits, in order to manage PFAS, to manage chemicals like PFAS. Everything essentially ends up in hazardous incineration. Employees are essentially protected not only by engineering but by the appropriate PPE. As far as the company strategy is concerned, we're now in a phase of needing to remove PFAS where we can. So it's identification, where we're using it. That has proved an extraordinarily painful activity over the past couple of years. Most of our supply chain, a lot of our supply chain will struggle to identify where they're using it. Justify its use. Do we need to use it? I mentioned historically we've all been lazy. We've used it where we don't need to. Now we have to justify. A VP's got to sign off if we're going to use it. Reduce where we can, eliminate where we should. And our current mission is to drive to a 2030 target where any new product after 2030 should not contain PFAS. That, I think, is an extremely tall order. But if you don't aim high, then you probably end up low anyway. So I think it's well worthwhile having the target. Education, I've mentioned my job is awareness. I think these guys are brilliant. This was one of our product companies in Korea who basically got their suppliers in. They have a PFAS task force. That PFAS task force then educated their suppliers on what PFAS were. They're also educating their employees. There are tours of their facilities to identify where PFAS are coming in, where PFAS are being used, where PFAS is being released. This is essentially where the regulations are going. You're going to have to do it. You're going to have to do it. So identification, where you have to use it, and then management is really going to be desperately important. So in summary, I think we've got there in good time. Basically, PFAS is everywhere in fabs. It's critical in etch, deposition and coatings, valves and pumps. The same traits that make PFAS useful also cause some problems in persistence, in bioaccumulation, toxicity and mobility. Health risks are real. Lots more research is going to be required. Regulators are tightening fast and inconsistently. But we have to live within regulations. Analysis and waste, there is a lag in technology. Only a fraction of the PFAS can be measured by speciation. And if you can't measure, then you can't treat. And industry must act, well, everyone must act, identify where you have to, remove it where you don't have to, design safer alternatives and manage waste to prevent environmental release. And that's me done. Thank you.
Thank you very much. That was wonderful. We had talked right before about the difference between, if you're trying to get rid of PFAS, would regulations help more, or would it help more if there was public outcry? And you already answered that, saying it depends on the region, but you want to say a little bit more about that?
Yes, what I'll do is I'll go by example. In Japan, there have been concerned citizens groups wandering around, measuring river water, and then putting the results into the press. And has every industry jumped? So that's a situation where actually concerned citizens are doing stuff. In other regions, it's much more done by the regulator, or so it's hit and miss. It's hit and miss. Some folks will have different priorities. It isn't a now problem for me. It isn't like putting food on my table. Although I perhaps shouldn't say that. But it isn't an urgent problem for most people, and therefore it will depend on region.
Yeah, super. Thank you. Any questions from the audience?
So when we think about PFAS, there are different definitions.
Yeah.
So for example, the EPA, an isolated C₃F₈ is okay. That's not PFAS. When you say about getting away from it, what definition? I mean, it seems. I mean, to me as a chemist, it seems hard to see a future without any carbon-fluorine bonds, right? And I'm just wondering, when you think about your transition 2030, what are the conditions you're putting on that?
As I said, the target that we set ourselves is extraordinarily aggressive. There are things that we are going to be able to do, hopefully relatively straightforward. There are things that are going to need some development in order to achieve certain goals, and that development to eliminate may take longer than 2030. Then I would step back to the advice that I was giving with regards to traceability. Know where you're using it, know what's going on, because clearly the equipment is not the only source. Know where it could be released, and essentially manage the touch points within the facilities that you operate, and make sure that those are not released. In the meantime, basically all companies are looking for short-term, medium-term, longer-term derogations and exemptions. Regulators are often not particularly enamored with exemptions, but will look for derogations for industry that can demonstrate, and it has to be demonstrated that you have to use it, that you have no options. The semiconductor industry is slightly handicapped by the fact that it is silicon-based, and therefore it is fluorine-based. One does wonder whether it's an opportunity for non-silicon semiconductor industry to be developed that's not reliant on fluorine, but that's just speculation. I think I agree with you. It's going to be very difficult to imagine an industry in the near term without some form of carbon fluorine polymers sitting somewhere. But they will need to be managed. In the meantime, the research needs to be done to identify what's really truly important. The number of research articles are increasing really quite dramatically, but the numbers of chemicals concerned are vast. So getting the information in the right place, getting the good quality information in the right place is important. But then I go back to, if we are still hampered by analysis lagging behind need, then a lot more effort needs to be expended, or I guess I'm saying money needs to be expended in the direction of standardized analytical techniques that are available. I mentioned during the talk that we're certainly struggling to get gas phase analysis done at reasonable cost. So these techniques need to be available not just to the likes of ourselves, but also in other countries. None of these research papers are coming out of less developed countries. And if mobility and bioaccumulation has essentially resulted in global distribution, then we need to be paying attention there as well.
Answer your question? Yeah. While I'm walking there, quick question. You talked about other material systems, maybe 3,5s and so on, that may not be as heavily reliant on fluorine like silicon is. Also, there are other sectors like firefighting foam and other industries that also are contributing to PFAS. So maybe we as the leaders in the semiconductor industry can teach how to move away from PFAS.
You'll notice when I went through the regulations, what I said was as it's getting closer to us, so the regulations become more stringent. Firefighting foams is a case in point. Cosmetics is a case in point. Surfactants that you place on your carpets, anti-stain, is a case in point. Anything that comes in contact with the public is essentially where the regulators are going to start. But if the materials are so mobile, then consideration needs to be given to the rest of industry. But you're absolutely right. It's a very broad topic. We'll be a very small emitter in the grander scheme of things, but we have to play our part.
In essence, my question was tapping on just that, so it nicely builds on it. I was wondering to what degree you felt comfortable to offer a comment on a figure of merit towards human health that identifies the biggest industry contributors.
I didn't quite catch the whole question. Could you repeat that again? Sorry.
How you would define a figure of merit towards human health that would identify the biggest industry contributors as a PFAS risk to human health. So to clarify a little bit as a point of comparison, what I'll say, we have read in the news over the span of the last year the discovery that the processing of human waste to create fertilizer has inadvertently generated PFAS.
Yes.
And there I was curious to understand the volume of PFAS generated and consumed per human annually from that source, in contrast to interactions with PFAS waste generation from fabs in the aggregate across the planet, right? Who's the bigger contributor of PFAS that's ending up in human bodies? Maybe it's too difficult to question, but I'm curious to what degree you would try to begin the process of quantifying that.
The process of quantification, given the disparate sources, the fact that the sources can be quite mobile, and I don't just mean mobile over long distances. It's going to be a challenge. Total consumption data, I think, we're probably already gathering, but only in certain countries. Yes, you can probably look for hotspots near likely sources, likely release points, likely historical release points, and that is certainly what the Japanese did. I'm not an enormous fan of essentially going for the finger pointing. I would much rather know exactly what the scale of the problem was and then start trying to solve the problem. However, if it's an ongoing problem, then there's a challenge.
Yeah, I know we're running out of time, so thank you so much for an interesting talk. I have one question that is pretty much two. The first one is about number 5. So do you see any promising scalable approaches? And are we talking about more chemistry-based, photonics and electronics could play a role or not? So what do you see around like any measurement things? And the second part of the question is, you're mentioning even in your talk from awareness to action. So the first action is, of course, education, and we're doing that from MIT, universities like Bridgewater, etc. But how to involve community? Because this gets really complicated pretty fast, and it has, like as Sajan was mentioning, a lot of complicated figures of merit and numbers, and what is the public policy we need to push for, and things like that. So it's complicated. Do you have any enlightenment there?
On the analytical side, I have nothing to offer. Yes, I'm an electroanalytical chemist, but I wouldn't necessarily be using electroanalytical methods to do this sort of analysis. I do follow the methodologies. I'm very much a fan of looking for trouble, because if all you want to do is believe numbers that come out of a machine, I think you're going to be really disappointed. So I don't have very much to offer on technologies, but I'm rather willing to test them, which is why in Q1 next year we'll probably be doing some time of flight mass spec on the gas phase, which will be interesting to see. And we've obviously got more testing to do on the liquid phase. Sorry, what was the other question? Can you remind me?
Education, action.
Education. So, well, yes, I'm here. Yes, we do it with our suppliers. I think educating your supply chain is really vital. I more than loved a bit what happened in Korea, what the guys did in Korea. That was brilliant. And more of that should be done. More outreach to the general public should be done. But that should be for all industries, not just for ours. And then I do go back to educate to employees. Again, that was something they did at our Korean site. I think that was great. So that educational aspect, I think, yes. If you don't know, you're not going to ask and you're not going to solve the problem.
Great. Thank you very much. Any other last questions before we let Dr. Chris Jones go? No? Great. Thank you so much. Really appreciate it.
Thank you.